Last time we looked at limits using tables and graphs, which are okay strategies, especially if you're only given a graph. There's not a whole lot you can do there. Today we're going to look at using some algebra techniques to evaluate limits, which is going to be much more useful for us going forward as we start talking about derivatives, instantaneous rate of change. So first of all, if you have a limit, like this one here, we're going to have the limit as x approaches 2 of x squared plus 5x plus 1. And the function exists at that point. It has a set value. If I take 2 and put it in here, I'm not getting any errors or anything undefined. I get 2 squared plus 5 times 2 plus 1. So I end up getting 4 plus 10 plus 1, 15. So f of 2 exists here, and it's 15, and that is what our limit is. Okay, our limit as x approaches 2 of this particular function is equal to 15. And you get an idea here that if you have a continuous function at this point, at x equals 2, then to evaluate the limit, we're going to be able to do a direct substitution here. We're going to put the 2 in for x and evaluate what our function is at that particular point. That's something you should always consider when you get a limit problem, because there might not be a lot of work to do. It could just be that you have to plug the number in and go with it. So this is more typical of a problem that you're going to see. We have the limit as x approaches 4 of 2x squared minus 7x minus 4 over x minus 4. And this is problematic if we think about the function at 4. We try and put 4 in here, we get a denominator of 0. That's bad, that makes it undefined. You can't divide by 0. It's the ultimate math sin, right? So our goal in the problem becomes eliminating this factor. We want to eliminate this issue from the problem. Okay, our problem is we put 4 in there. If we can get rid of that factor of x minus 4 in the denominator, then we will be all set. So I'm going to try here to factor the numerator and just see what happens. Okay, and I'm just going to guess here that maybe one of my factors in the numerator is going to be an x minus 4. It's usually a pretty safe guess when we're dealing with book caliber limit problems. And then that would make this other factor 2x plus 1. So I've got 2x squared minus 8x plus 1x. That's getting me the minus 7x. And then I've got minus 4. Okay, so what's happened here is I've got an x minus 4 that I could cancel out. Now, this type of evaluation is not quite legal when we're dealing with just regular functions, but if we're considering it as a limit and we want to know what the limit is, it's basically telling us here that our regular function would be a straight line. It would be 2x plus 1, and then at x equals 4, we'd have a hole in the graph. Our limit then becomes our hole filler, okay? Now we can actually evaluate what this limit is. We can put 4 in and get a number out. So when we get to this point, we're now evaluating the limit, and when we're evaluating the limit, we don't write that notation out front anymore. We can put the 4 in, so we've got 2 times 4 plus 1, and we find that our limit in this situation is 9. So again, that's saying that once I eliminate that factor, I can see that this function is going to act just like 2x plus 1. There's going to be a hole at 4, and 4, 9 would actually be the hole filler. Okay, I would have a graph that looks something like this, and then at 4 there would be a hole. And so the y value that this graph would be approaching as x is equal to 4 would be 9. That's our limit. Our function is undefined at that point, but our limit is equal to 9. Okay? So that's one type of very common limit where we factor the numerator and we can do some cancellation. We can cancel out a common factor. Another very popular limit type problem involves square roots. So here I have the limit as x approaches 5 of the square root of x plus 4 minus 3 over x minus 5. Again, this is problematic because if we try and take 5, put it into the denominator, we get a denominator of 0, and we cannot do that. We can't divide by 0. So nothing really here to factor in the numerator, so we're going to have to try a different strategy. Okay, so we have a square root. Maybe if we can somehow eliminate that square root, we can eliminate the factor down here. So what we are going to do on this problem is rationalize the numerator. Now you might remember the term rationalize from pre-calc days. Rationalize, we're looking to get rid of radicals here. We're looking to write the numerator without a radical in there and hope that maybe something will cancel out. In pre-calc, you tend to rationalize the denominator. Okay, here we're going to rationalize the numerator, and we're going to do that by multiplying by what's called the conjugate of the numerator. So I've got square root of x plus 4 minus 3 over x minus 5. I'm going to multiply the top and the bottom of my fraction by the conjugate of the numerator. So I got square root of x plus 4 plus 3. And at first glance, that might make it look like I'm making the problem worse, that I'm increasing what I have in the denominator, and how is this ever going to work out for me, okay? But just let it play out here, okay? So we've got the limit as x goes to 5. When we multiply in the numerator here, we've got the square root of x plus 4 times the square root of x plus 4. If we multiply a square root by itself, we end up with just what's inside, so x plus 4. The middle two terms in the numerator are going to cancel each other out. So I've got 3 times the square root of x plus 4. And then I've got minus 3 times the square root of x plus 4. And then I have a minus 9 on the end. So why the rationalizing the numerator technique works, why we multiply by the conjugate, is we're artificially creating the difference of squares. And when we create the difference of squares, middle terms cancel each other out. Now, I am not going to multiply through on the bottom because my ultimate goal here is to get rid of this x minus 5. So I'm going to keep that in there in its factored form and not multiply it through to create more havoc. Now, when I've canceled out these middle terms, I'm left with x plus 4 minus 9, which, shocking, I know, ends up as x minus 5. And there is our x minus 5 that we need to cancel. And of course, these problems are structured in a way that this is going to work out. Now, the good side of that is when we start working with derivatives, the derivative problems are also structured in a way where it's going to be nice and clean for us. So the x minus 5's cancel. When I cancel a factor like that in the numerator, it doesn't blow the numerator up. It's still there, okay? And so there's still a factor of 1 left behind. Now I'm going to take my 5, and I can evaluate this limit because this factor is not going to be 0. So when I take 5 and I plug it in, I've got 1 over square root of 5 plus 4 plus 3. Notice when I'm doing this step, I'm removing the limit from the front. I'm evaluating the limit at this point. I'm putting 5 in. So I've got 1 over the square root of 9 plus 3. And so my limit here is 1 over 3 plus 3. It's 1/6. Okay? So that's, again, a very common type of problem when we're talking about evaluating a limit. Okay, another problem to take a look at. Let's say we have the limit as x goes to 0 of 1 over 5 plus x minus 1/5 over x. Trying to get rid of the x, if we put 0 in here, that would be bad. I always like to approach these problems as what could I do? I'm going to try something. And I see some subtraction that I could potentially do in the numerator. So let's try and combine this into one single term and see what we can do. So to get a common denominator in the top part of this fraction, I'm going to multiply here by 5 over 5. And I'm going to multiply my second fraction by 5 plus x over 5 plus x. I still have a denominator of x. Something I've noticed with students over the years where they end up making mistakes with this is they try and get cute and write the numerator off to the side, and then they lose track of the x because they forget about it. They don't write it down. They're just kind of all over the place with the writing. Especially when you first are working with these limits, write each step down, take the time to show what you're doing, and give yourself a path backwards to follow if you get stuck. So on top here, I have 5 over 5 times 5 plus x minus 5 plus x over 5 times 5 plus x over x. Now when I subtract here, I have 5 minus 5. I also have to be careful to subtract the x. 5 minus 5 is getting me 0. So in the numerator here, I end up with negative x over 5 times 5 plus x. My denominator here, when I'm dividing by x, that's the same thing as multiplying by 1 over x. And when you write it that way, you can see here that we have some cancellation that can take place. I can cancel out the x's. That's really what's giving me the problem with this limit as x goes to 0. So I've got the limit as x goes to 0 of a negative 1 over 5 times 5 plus x. Now I'm evaluating my limit by putting in the 0 for the x. So I've got negative 1 over 5 plus, or 5 times 5 plus 0. So I got 5 times 5, which is negative 1 over 25. Okay. So these are some early strategies for evaluating limits. We have factoring, we have rationalizing the numerator, and then if we have fractions inside of a fraction, we can try and add or multiply or do something to simplify the numerator to see if we can get it to cancel out what's in the denominator.